Welcome back to part 2 of Forces in Motion. That's the CP2 topic of Edexcel Physics GCSE. We're going to pick up where we left off, and we're moving into the section that deals with stopping distances with cars on a road. That links in with human reaction times, factors that affect how quickly a car can brake, because obviously there's two parts to a car braking. There's the person driving it, and there's the actual car itself. So let's look at some typical questions and answers to that. First one, what is the length of a typical human reaction time? This is just a number that we just have to know. It's approximately 0.3 seconds. There might be a little bit of leeway with that in the exam, but I would just memorise that number. Give 3 factors which affect the thinking distance and the braking distance. Well, these two components of stopping distance are the distance that the car travels whilst the human is actually thinking about braking. So what factors will affect how quickly someone will be able to react before they then put the brakes on? In other words, the distance they travel whilst they're thinking. Pause the video and see if you can come up with at least 3. Okay, so thinking distance can be anything which affects your reaction time. So things like drugs, alcohol, and distractions such as mobile phones. There's quite a lot to go through there. You can maybe have a look in your revision guide, pick up a couple more. For braking distance, well, these are factors which affect how quickly the car actually comes to a stop once the brakes have been applied. So the factors around that, well, you have a think. What could there be? Typical ones here are anything to do with friction, because friction is going to be the force which brings the car to a stop. So it could be the weather, but make sure you actually give an example. So, e.g., if it's icy, then it's going to be a lot harder to stop the car. Other things which affect braking distance could be the condition of the brakes or the condition of the tyres, which is why it's actually illegal to have tyres which have a tread below a certain size, because if you've got, as they're referred to, bald tyres, then you won't be able to get enough friction to stop the car within a reasonable distance, especially if it's wet. Define stopping distance. So for a definition, we just need to state what it is. So stopping distance is the thinking distance plus the braking distance. In other words, the total distance it takes to stop is the distance you travel whilst you're thinking, reacting to, I don't know, if something comes into the road, plus the distance that you travel whilst, after you've put the brakes on. So how long it takes for the car to actually come to a stop. Okay, part D. Explain why the thinking distance also depends on the speed of the vehicle. Use distance equals speed times time to help your answer. Again, this is an explain question, so we want to try and include the word because. So let's go back and recap what thinking distance actually is. Thinking distance is the distance you travel whilst you are reacting. Okay. So why does this also depend on the speed of the vehicle? The thinking distance is going to depend on your reaction time, but also it's going to depend on the speed of the vehicle, because I'm going to go through this answer in two parts. I'm basically going to explain why, given examples using numbers. So see if you can do the same thing. Include that equation and try and think of two situations and use numbers to show that the speed of the vehicle will actually affect the distance that's travelled. Have a go yourself. Okay, so we're going to pick a random speed. I'm going to say 10 meters per second. But we're also going to pick a time, which is the reaction time of a person. Well, earlier on we said that a typical reaction time is about 0.3 seconds. So why don't we stick with that? Let's calculate what the thinking distance would be if the speed is 10 meters per second. Well, if we're travelling at 10 meters per second and it takes me 0.3 seconds to react, then the distance is going to be 10 times 0.3, which is 3 meters. So the thinking distance in this case will be 3 meters. The car will travel 3 meters and then the human will put their brakes on. But what about if the speed changes? What about if they're travelling 50 meters per second? Well, distance equals speed times time. This time we've said, well, the car's travelling at 50 meters per second. And what time do we use? Well, let's use the same time, because we don't want to change that. We want to prove that it's only the speed that's causing the change in the distance. So we're going to use 0.3 seconds again. If we do that, then, well, we're travelling 5 times as fast, so we're actually going to get a distance of 15 meters. So to explain why, if this was a written question, we'd want to explain that the reaction time of the person stays the same, but if we're travelling at 10 meters a second, we only travel 3 meters in that time. But if we're travelling faster, then we're going to travel more distance in that time. And this is one of the big reasons why we'll have speed limits on the road. You know, it doesn't matter if your reaction time isn't super quick. Just a standard reaction time is going to affect your overall stopping distance, because you're actually going to travel 15 meters. If you're travelling 50 meters a second, you're going to travel 15 meters before you even put the brakes on. And obviously in residential areas, 15 meters could be the distance between you and someone stepping out. Last question as part of this topic. Using F equals ma, explain why a person in a fast moving car which hits a wall and comes to a quick stop may die. Have a think about this one and have a go yourself, and I'll go through it in a couple of seconds. Okay. What's important here is to kind of change the wording of the question so that it makes more sense to this equation. Using F equals ma, explain why a person in a fast moving car which hits a wall and comes to a quick stop may die. So we can think about what this means. If someone's going to die in a car accident, it's because there must have been a large force acting on them. What does a quick stop mean? A quick stop means there must be a large deceleration. And a deceleration is just a negative acceleration. So this A is going to be a very large number if you're in a car crash. So, as a written answer, we can say in a car accident, the car and the person are brought to a quick stop. This means there is a large deceleration. Now the A stands for the deceleration, acceleration, either way. So for a fixed mass, so if we think about a car and a person, the same car and person, if there's one car and person that comes to a stop slowly, then that letter A would be a small number. But if they stop quickly, then that letter A is going to be a big number, yet M is going to stay the same. So for a fixed mass, a car which stops quickly will experience a larger force than a car which stops slowly. Because it says using F equals ma, then I should actually try and put numbers into that equation. So let's take a typical mass of a car, let's say 1,000 kilograms. In this scenario, we've got a car, yes, that is supposed to be a car, is going to hit into a sponge and come to a stop. Now, do we think that's going to be a large deceleration or a small deceleration? Well, if you hit a sponge, the change in speed is actually going to be quite slow compared to the change in speed if you hit a concrete wall. So here, let's say that the acceleration is minus 5 meters per second squared. And in the concrete wall, because you come to a much quicker stop, let's say that the acceleration is minus 100 meters per second squared. So you're going to decelerate a lot quicker hitting a concrete wall. Then we can just state the mass in both situations. Let's say it's 1,000 kilograms. And we can see that the force in this equation, in this scenario, is 1,000 times minus 5. Which means the overall force to get that to stop at that deceleration is going to require minus 5,000 newtons. And that 5,000 newtons, the minus sign just means that it's acting that direction, against the car. Here though, we've got 1,000 and minus 100, so we're actually going to get the same mass, but this time minus 100. So the force experienced is minus 100,000 newtons. That force is going to kill someone. And so because of the bigger deceleration, using F equals ma, we can see that the force required to cause that to happen is large enough to kill. Okay, hope that helped. Next time on the Physics Bible, we're going to be looking at CP3, which is all to do with energy and energy transfers. So I'll see you there.